All right, let's work through this example to see some subtleties of our fundamental theorem of line integrals. So I'm considering this vector field H, and let's look at its component functions. Okay, and so from the notation of earlier, this would be the component function m, and this would be the component function n. And I know I have this check for conservatives, so I'm going to run through some partial derivatives and make some observations. Okay, I took the partial derivative of the first component function of the vector field h with respect to y, and I got this expression here. Let me do the partial derivative of the n component function with respect to x now. So look what I've discovered. I've discovered that the partial derivative of m with respect to y of this vector field h is the same as the partial derivative of the n with respect to x. But where is this valid? H is defined on the entire plane except for the point 0, 0. So I'm going to write it like this. It's defined on the entire plane except it's not defined at the origin. And visually, that means that the domain of this vector field is like the entire plane with the origin removed. So geometrically, I'm going to imagine it as like, this big donut with a tiny little donut hole poked out of the middle. So let me come back up here to my check for conservative and think about what I've just discovered. Okay, here is my check to see if a two-dimensional vector field is conservative. If the partials that I just took are equal and the region over which the vector field is defined is simply connected. Here's a problem because this check of conservative, or whether the vector field is a gradient or not, is only valid if my vector field is defined over a simply connected region. And remember what simply connected meant. Simply connected meant it couldn't have any holes in it. So I have no information about whether this vector field is conservative or not. And in fact, I'm going to go through and compute a line integral as instructed, and I'll be able to deduce, in fact, that this vector field is not independent of path. So I'll, from that, understand that indeed my vector field wasn't conservative in the first place. And then I'll answer the question about the fundamental theorem of line integrals. Okay, so I've gotten nothing from this check. No conclusion about conservative. Okay, but they do want me to compute the line integral of this vector field over a unit circle oriented counterclockwise. Well, I can do that because I can parameterize a unit circle. So I'm going to go through that computation. This standard parameterization of the unit circle runs counterclockwise. Okay, I am now going to compute the line integral of the vector field h over the curve C, which is the unit circle counterclockwise. All right, so I've set up my line integral in an old school fashion. I had to parameterize the curve, plug the parameterization into the vector field, and dot that with r prime, and I'll just work out the integral from there. Notice that x squared plus y squared here is 1. Okay, I'm left with an integrand of sine squared plus cosine squared, which is of course 1. So my integral's value is 2 pi. And what can I say about this result? What this means is the value of the line integral not being 0 across this closed curve, that means that the vector field itself is not path independent. If the integral was path independent and we had a conservative vector field, then the value of that line integral would be the potential evaluated at the starting minus the potential evaluated at the ending point. But those would have to be the same value since the curve is closed starting where it ends, and the value of the integral would therefore be 0. But instead I've gotten a value of 2 pi out. And so this does not contradict the fundamental theorem of line integrals, because the fundamental theorem of line integrals says something about conservative vector fields. They say if you have a vector field that is the gradient of some potential function, then you're going to have the path independence and that fundamental theorem holding. I went through the check of my vector field because I thought that might help me figure out if it was conservative, but there's this very small subtlety here that the partial derivatives here are equal to each other, but not on a simply connected region. So it's actually the fact that this closed curve circles the hole in the region that we're getting this discrepancy here in the line integral. In fact, if you had a closed if you had a closed curve that didn't circle the hole and you integrated the vector field across that, you actually would get 0 as an answer. But here I'm not getting 0. My vector field is not conservative. And so I'm not contradicting the theorem. Okay, let's, for some more practice, go through another example of computing the line integral of a vector field across a curve. And I'm going to do a real quick check here to see that this vector field is conservative. So let me remind you of the check for 3 variable functions. Okay, so if my vector field has component functions m, n, and p, and the vector field is continuously differentiable across a simply connected region in 3 dimensions, then this check will tell me whether it's conservative or not. Well, f has polynomial component functions, so it's definitely going to be continuous and differentiable everywhere. So it is, whatever. The check is going to go through since the domain of this vector field is R3 in its entirety. So let's go ahead and take the partial of m with respect to y and observe that that's exactly the same thing as the partial derivative of the n function with respect to x. Okay, so that one's checked. Let's take the partial derivative of the m function with respect to z now. We get y. And notice that's the same as taking the partial derivative of the p function with respect to x. Okay, so that's checked. And then finally, let's take the partial derivative of the n function with respect to z, and we get x, and observe that that's the same thing as taking the partial derivative of the p function with respect to y. Okay, so in fact, f is conservative, which means I should be able to find a potential function for it. With f being kind of simple, I think I'm going to do this in my head, but you can go through a systematic process that I outlined before if you like. You can integrate m with respect to x, integrate n with respect to y, and integrate p with respect to z, and then line them all up. But if I look carefully, I see that the expression xyz is something that when differentiated by x, you get this, by y, you get this, and by z, you get that. So sort of just by inspecting the components carefully, I see that this is exactly the 3 variable function I need to get these partial derivatives. So this right here, fxyz equals xyz, is a potential function for f. So the gradient of f is the vector field. Okay, and I can use my my fundamental theorem of line integrals then to compute the work done going from A to B along any curve that connects A to B. So I got my point A, I got my point B. Pretty much any curve will do because the conservative vector field is path independent. So all I need to do to compute this line integral, which of course represents work, is after making the observation that the vector field is the gradient of this function xyz, all I'm going to do is plug in the point B, plug in the point A to my potential, and that's the value of the line integral. Okay, so my f is right here, x times y times z. The point B is 358. So there, I just plugged in 358 into the function, minus the point A is 1, 2, 3. So I'm getting 120 minus 6 is 114. Done.